Now we can go over an example of actually getting the CNF form and using the SAT solver. I'm going to design a very simple circuit for now. I'm going to assume I have two inputs, A and B. This is an AND gate. I have an output here, and I have an OR gate here. And then I have an output. So when we do this, it's very useful to assign intermediate variables. So A, B, I'm just gonna call this C, and I'm gonna call this D. And since we know we will be using a different circuit and checking whether they are equivalent or not, it makes sense to use an index 1, 1 here. So this is the C for circuit 1, this is a D for circuit 1. We are going to be using the same input, so there is no need to put an index for the inputs. So this is C1, this is circuit 1. Circuit 2, it can be the same, it can be different. I'm gonna assume it's the same for now. So this would basically be 2, 2, D2. Now, this is OR. Sometimes we ask you to change one gate and then redo the analysis. So you're basically like gonna change this AND or this OR and then check again, okay? So what do we do now that we have two circuits, C1 and C2? We want to use a SAT solver to check whether those circuits are equivalent or not. We have an output, D1, D2, and we're just gonna follow the same steps. We need to get the characteristic relationship that captures the schematics of the first circuit in CNF form, and characteristic relationship for the second one in CNF form, and then include the validity check and give the input to the SAT solver. Let's just take it one step at a time. I'm gonna work with circuit 1 for now. Characteristic relationship for AND. So I'm just focusing on this part here. Okay, so I can say that C1 is equivalent to AB. And then I can further simplify this, as this means that C1 implies AB and AB implies C1. And we can simplify this further. C1 implies AB means that not C1 or AB and not AB together negated or C1. Now we can split this further, so I have not C1 or A ended with not C1 or B. I just split the first one into those two here. And this is ended with not A, or I'm just using De Morgan here. Not, if this is confusing you, please review De Morgan, or C1. So that's basically the CNF form characteristic relationship for the first AND here. Okay, so now we can redo this for OR, CR OR equals. I have D1 is equivalent to B or C1, right? We can further simplify this. D1 implies B or C1, and I'm running out of space here. And B or C1 implies D1. And we can further simplify this as not D1 or B or C1 and not, again I'm just using De Morgan here, not B and not C1 or D1. And then we can further simplify this. I'm just gonna use more space. The first one is already in CNF form, not D1 or B or C1, and it was not B. I'm just gonna move this to the next part. So not B or D1 and not C1 or D1. Let me just double check. Not C1 or D1, not B1 or B or D1. Perfect. So now I have the characteristic relationship for and or. So what's the characteristic relationship for C1 altogether? So CNF, we know this is in CNF. Characteristic relationship for C1 together is CR and it with CR or. So that will basically be this first part here. Ended with this second part here. Now, if we assume that circuit 2 is the same one as circuit 1, then we can just say that we know that the characteristic relationship for CRC2 will be the same thing, except the index will be 2 instead of 1. So we can just make this 2. Okay, so now we have the CNF form for C1 and C2. And of course, this is in the case they are equivalent. If they are not equivalent and you changed one of those gates, then you need to do the analysis again for C2. This will be different, they will not be the same. So in that case, you will get the new CNF form for CR2, for CR for C2 I mean, and then you will have the two expressions in CNF form. So what do we give the set solver? We need to encapsulate the whole comparison in one CNF expression. So we're gonna say CNF for circuit 1, characteristic relationship for circuit 1, ended with CNF for characteristic relationship for circuit 2, ended with, we can say, we have two outputs here, D1 and D2. And we want to check whether D1 is equivalent to D2 or not. Okay, so why the negation? Well, it's very important to understand this part. Please take your time, but try to understand this part very clearly. Why do we negate this? So I want to check whether D1 equals D2 or not. Okay, how does the set solver works? It's going to try to find the first one that it satisfies the equation, the whole thing, right? Once it finds one that satisfies the equation, it's gonna call it satisfiable. Satisfiable means it can be satisfied. It does not mean equivalent, right? So if I tell you that this equation can be satisfied, is this enough to tell that they are equivalent? No. It might just be that, one set of arguments was satisfied, but for other set is not satisfiable. It's not the same. Like, I don't know how to explain this, but satisfiable means it can be satisfied once. It does not mean that the two circuits are always going to be satisfiable. Always means valid. Always satisfiable. Always satisfiable is not the same as satisfiable. So what do? We negate the solution. We negate the expectation. I'm gonna tell it, okay, I wanna check if they are ever not the same. If they are ever not the same once, that's enough for me to say they are not satisfiable, because there is at least one time where those two outputs are different. So this is unset. And unset here, I'm sorry, if it's satisfiable at least one. If it says set, it means it's satisfiable at least once. This means they are inequivalent. They are not equivalent, right? Because there is at least one time where they are not satisfiable. So many students told me I'm gonna use an XOR gate at the end. Please don't use an XOR gate at the end. Just this is the meaning. This is an XOR gate, basically, right? But don't add a physical XOR gate into the design, because we're not adding a physical XOR gate into the design. When we used VC formal to check whether two circuits are equivalent or not, we did not add an XOR gate into the design like this. This is basically the validity check we're adding, but we're not physically adding it to the circuit. It's just a notion. We're communicating to the SAT solvers that we're looking for at least one instant in which D1 and D2, the two outputs, are not equivalent. Why are we not checking for equivalence? Because they might be equivalent part of the time, but not all the time. So we reverse the problem to check if they are ever not equivalent, because if yes, then that's satisfiable, and that means they are not equivalent. Because if they are equivalent, we expect them to always be equivalent. Okay? So then what do we input as what do we give to the SAT solver? So first we can simplify this. D1 implies D2 more. This is a small exercise, you can work on it on your own, but D1 implies D2. I'm just gonna remove this negation on the side, and D2 implies D1. But basically, eventually, what you will get here will be D1 or D2, and not D1 or not D2, which basically is an XOR, right? But again, we did not physically add an XOR. This is just a term we're adding to the input of the SAT solver to communicate what we're trying to check. This can be different in other examples. It doesn't always have to be an XOR, okay? And if you have multiple outputs, this will be different again. So please don't physically add an XOR to the circuit. Okay, so what will be the input to the SAT solver? We need the CNF form for CR characteristic relationship for circuit 1. This is going to be ANDed with CNF characteristic relationship for C2. And this will be ANDed with our validity check, which is this. So in our case here, this is quite simple because we know this is the CNF form for C1. And I'm gonna add an AND here, and I'm gonna get the CNF form for C2. Oops, sorry. And we also need to add this validity check at the end. So now we have an expression that is completely, entirely in CNF form. It includes C1, it includes C2, circuit 1 and circuit 2, and it includes us telling SAT solver that we're looking for any instance where these two outputs are not the same. Once you have this, you are ready to go pick a SAT solver. There are many. To input this and see whether you get SAT or unsat. SAT means the outputs can be different, so it means the two circuits are not equivalent. Unsat means we can never satisfy first output not being equal to second output, so it means that they are always equal, so it means that the circuits are equivalent. Now when you use a SAT solver, each SAT solver can be different, but the way you input this into the SAT solver, I guess I'll make another video on how to do this. It's not hard, it looks hard, but it's not really hard. We're gonna count how many laterals or how many variables we have. We're gonna count negation and not negation as the same variable. And we're gonna count how many clauses we have. So for example here, let's try to do as much as we can here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I have 14 clauses here. Actually, let me remove this quickly. We said 14, right? Yeah. And then how many variables? Well, I know I have A and B, and I have C and D, but I have C1, D1, C2, D2. You can double check. I don't think there are anything else. So we have 6 variables total. So I expect I will have 6 variables, 4 clauses. If I have A, you can map them any way you want, but I'm just gonna say A, B, C1, D1, C2, D2. I'm gonna call A1, B2, C3, D4, C2 is 5, D2 is 6. If I have A negated at any time, it's just gonna be -1. If I have B negated, it's gonna be -2. If I have C negated, it's gonna be -3, and so on. So it's gonna be the same number just with a negative. This is a notation for negation. Now we expect those two circuits to be equivalent, right? Because I haven't changed anything. And for them to be equivalent, I'm expecting to get unset. We're gonna try this in the next video, but as you've seen in our assignment, we're asking you to change one of the gates, redo this. You'll just need to change the CR/C2. This term will be the same, but this green part will be different. And then you'll prepare the input for a set solver and check whether they are satisfiable or not.